Hello friends, I welcome you on my channel Engineering Mathematics djganit. In this lecture we will do some more examples on Taylor and Maclaurin series of complex functions. We start with this first example. Find Maclaurin series of function 1 over 1 minus z, and we will show that Maclaurin series of this function is nothing but geometric series in complex variable z. So this is the example in which we have function 1 over 1 minus z, and we will show that this function has Maclaurin series, which is geometric series in complex variable z. So as we know, first we have to decide the validity of Maclaurin series. That is, we have to decide the region in the complex plane in which this function has Maclaurin series. So first we consider, suppose f of z equal to 1 over 1 minus z, and we know that this function is not analytic at z equal to 1, and it is analytic at every point except z equal to 1 because it is a rational function. So suppose we have z equal to 1 somewhere and we are interested in the Maclaurin series, so center of this series is 0. Now this function is not analytic at z equal to 1 only. So if we consider the distance between 0 and 1, that is distance between center and the point at which function is not analytic, is 1. So we can say that this function is analytic in the disk which is represented by absolute value of z minus 0 is less than 1, that is absolute value of z is less than 1. So if we consider circle with center 0 0 and radius 1, suppose this is the rough sketch of circle with center origin and radius 1, then this function is analytic at every point inside this circle, and the region which is inside the circle is nothing but open disk with center 0 and radius 1. So this function is analytic in this open disk. Therefore, by Taylor's theorem, we can find out its Taylor series with center z equal to 0, which is valid in this open disk. So now to find out Taylor series at z equal to 0, we have to first find out values of function and its derivatives at z equal to 0. So f of z is 1 over 1 minus z. So f of 0 is 1 over 1 minus 0, that is 1. Now first derivative of 1 over 1 minus z is minus 1 divided by 1 minus z square into derivative of 1 minus z, which is 0 minus 1. So here we are applying chain rule for finding derivatives. So this negative negative positive, and we have 1 over 1 minus z square, and therefore first derivative at 0 is 1 over 1 minus 0 square, that is 1 square, and therefore it is 1. We find out second derivative. Second derivative of f of z is nothing but derivative of f dash z, which is minus 2 divided by 1 minus z cube into derivative of 1 minus z with respect to z. So it is nothing but minus 1. So this is going to be positive, and we are left with 1 minus z whole cube. So therefore second derivative at 0 is 2 over 1 minus 0 cube, that is 2. Then we calculate third derivative. Third derivative of f of z is derivative of this two constant. Derivative of 1 over 1 minus z cube is minus 3 over 1 minus z raised to 4 into derivative of 1 minus z, which is minus 1. So this is going to be 2 into 3, that is 6, divided by 1 minus z raised to 4. And if we substitute z equal to 0, we have third derivative equal to 6 divided by 1 raised to 4, that is 6. So in this way we can calculate higher order derivatives, but we go up to third derivative here, because if we go up to third derivative we have 4 non-zero terms. Now this function f of z equal to 1 over 1 minus z, as we discussed, it is analytic in open disk represented by mod z less than 1. So therefore we can find out its Taylor series about z equal to 0. So by Taylor's theorem, we have the formula for Taylor series about z equal to 0 or Maclaurian series. Second derivative at 0 divided by 2 factorial z square plus third derivative at 0 divided by 3 factorial z cube, and so on. And as we discussed, this is valid in open disk mod z less than 1. Now we substitute values of function and its derivative at z equal to 0. So value of function at z equal to 0 is 1, f of 0 is 1, and f dash 0 is also 1. F of 0 is 1, f dash 0 is 1, so we have 1 plus z. And here we have 2 factorial, that is 2, and second derivative is 2, and third derivative is 6. So second derivative is 2 into z square, third derivative is 6, and 3 factorial is also 6 into z cube, and so on. And this is valid in the open disk mod z less than 1. Now we substitute f of z equal to 1 over 1 minus z, and here 2 will cancel out, so we have z square. Here 6 will cancel out, so we can see we obtain geometric series as a Maclaurian series of this function 1 over 1 minus z. So in this way we can find out Maclaurian series of this function, which is valid in the open disk mod z less than 1. And we will remember this Maclaurian series of 1 over 1 minus z. So Maclaurian series is easy to remember. Here first term is 0 power of z, that is 1. Then we are increasing powers of z, so 1 plus z square plus z cube. So this is geometric series because if we take ratio of any two consecutive terms, then it remains same. So this is geometric series, and it converges to the function 1 over 1 minus z for all z which are in the open disk mod z less than 1. Now we consider this example. Find Maclaurian series of f of z equal to 1 over 1 plus z square. Now this function is rational function, and it is not analytic at those points z at which z square plus 1 is 0. So this implies z square is minus 1, and that is z square equal to I square. So from this we obtain z equal to plus or minus I. Suppose I put z equal to I will have I square, which is minus 1, and minus 1 plus 1 is 0. And if I put z equal to minus I, then minus I square plus 1, that is going to be I square into minus 1 square plus 1, this is 1 and I square is minus 1. Okay, so for z equal to plus or minus I, this denominator becomes 0. So this function is not analytic at z equal to plus or minus I. And we are interested in the Maclaurian series. So center of the series is z equal to 0. And the points at which this function is not analytic are I and minus I. So distance of center from these 2 points is nothing but 1. If we consider the distance between 0 and I, which is minus I, then it is 1, and similarly distance from 0 and minus I is also 1. So we consider this circle with center 0 0 and radius 1. So these 2 points at which function is not analytic are outside the disk. Absolute value of z is less than 1. These 2 points are on the boundary of the circle mod z equal to 1. So we are not having any points inside the circle mod z equal to 1 at which this function is not analytic. So that means this function is analytic at every point in the open disk. Absolute value of z is less than 1. So therefore we can talk about Taylor series of this function at z equal to 0 in the open disk mod z less than 1. Now one way is to find out value of function and its derivatives at z equal to 0 and then use the formula for Maclaurian series of given function. But we are not going in that way. Here we will use the Maclaurian series of 1 over 1 minus z. We know that Maclaurian series of 1 over 1 minus z is nothing but 1 plus z square and so on. And this is also valid in the open disk mod z less than 1. So here instead of minus z we have z square. So this 1 plus z square we can rewrite as 1 minus z square. And if we compare with 1 over 1 minus z, we have instead of z we have minus z square. So in the Maclaurian series of 1 over 1 minus z, we will replace z by minus z square to obtain Maclaurian series of 1 over 1 plus z square. And we have shown that this function is analytic in this open disk with center 0 and radius 1. So first we mention that f of z equal to 1 over 1 plus z square is analytic in the disk, or we can write open disk mod z less than 1. Now we know that we will remember the Maclaurian series of 1 over 1 minus z. It is very useful Maclaurian series. We are going to use it frequently in writing Maclaurian series of some other functions. So as we know, this is also valid in the open disk mod z less than 1. So in this series we replace z by minus z square so that we obtain 1 over 1 plus z square. So replacing z by minus z square, we write one more step, 1 minus z square. Here we write minus z square plus minus z square square plus minus z square cube and so on. And as we discussed, this is also valid in the open disk mod z less than 1. So this we can rewrite as 1 over 1 plus z square. Here This is 1 minus z square. Square of minus z square is z raised to 4. Cube of minus z square is minus 1 cube, which is minus 1 into z raised to 6, and so on. So this is nothing but Maclaurian series of 1 over 1 plus z square. So if we use this standard Maclaurian series, then we can easily obtain the Maclaurian series of 1 over 1 plus z square. We consider one more example. Find the Maclaurian series of f of z equal to arc tan z, that is inverse tangent function. F of z is nothing but tan inverse z. So to find out Maclaurian series of tan inverse z, we can go by directly the formula of Maclaurian series, or another way is we have f of z equal to tan inverse z. So first we take derivative of tan inverse z, which is 1 over 1 plus z square, and then we find out Maclaurian series of 1 over 1 plus z square. So as we have done in the previous problem. So to find out Maclaurian series of 1 over 1 plus z square, we write it as this, and then we use the Maclaurian series of 1 over 1 minus z. So as we did in the previous example, we are using the Maclaurian series of 1 over 1 minus z. We know that 1 over 1 minus z is 1 plus z square plus z cube, and so on. So therefore here we have 1 plus minus z square plus minus z square plus minus z square cube, and so on. And because this is valid in the open disk mod z less than 1, this is also valid in the open disk mod z less than 1. So we are using the standard Maclaurian series here, 1 over 1 minus z. Now we simplify this. F dash z is nothing but 1 minus z square plus z raised to 4 minus z raised to 6, and so on. This is valid in the open disk mod z less than 1. So we obtain the Maclaurian series of derivative of f of z, but we are interested in the Maclaurian series of f of z. So we integrate both sides with respect to z. So integrating, we get, so on the left hand side we have integral of f dash z with respect to z, and here integral of this 1 minus z square plus z raised to 4 minus z raised to 6 dz, and plus constant of integration, where this c is constant of integration, or it is arbitrary constant. Now integral of f dash z is f of z. Integral of 1 with respect to z is z. Integral of z square is z cube by 3. Integral of z raised to 4 is z raised to 5 by 5, minus z raised to 6 has integral z raised to 7 by 7, and so on, plus constant of integral. Now our function is f of z is nothing but tan inverse z. So if we consider a value of function at 0, then we have tan inverse 0, which is 0. So we can use this condition f of 0 equal to 0 in this equation. So using f of 0 equal to 0 in star, we obtain, on left hand side we have f of 0, that is 0, and here everywhere we put z equal to 0. So every term contains z, so we obtain 0 because there is a z in each term. So we have 0 plus c, therefore constant is 0. So using c equal to 0 in star, we have f of z equal to z minus z cube by 3 plus z raised to 5 by 5 minus z raised to 7 by 7 and so on. And f of z is nothing but tan inverse z. So we have obtained the Maclaurian series of tan inverse z, which is valid in the open disk mod z less than 1. So in this example, to obtain Maclaurian series of tan inverse z, first we are taking derivative of tan inverse z, and then we obtain derivative as 1 over 1 plus z square. So we obtain Maclaurian series of 1 over 1 plus z square using the Maclaurian series of 1 over 1 minus z. Then we obtain f dash z, we obtain the Maclaurian series of f dash z, and to obtain f of z from f dash z, we are taking integration, and to find out the value of constant, we are using the fact that value of tan inverse 0 is 0. So if we go in this way, we can easily obtain the Maclaurian series. Suppose we are going by the formula of Maclaurian series, then first we have to consider derivatives. So first derivative is 1 over 1 plus z square, then second derivative is minus 1 over 1 plus z square into 2z, that is minus 2z over 1 plus z square. Then in the third derivative we have to apply division rule because we have function of z in the numerator and denominator also. So instead of going in this way by using derivatives or by using the formula of Maclaurian series, it is easy to obtain the Maclaurian series in this way. First we are taking derivative of tan inverse z, then we are finding the Maclaurian series of derivative, and after integrating the Maclaurian series of derivative, we obtain the Maclaurian series of tan inverse z. So in this way we can use standard Maclaurian series to obtain the Maclaurian series of other functions. So this is all about today's session. I hope you like this lecture. Thank you very much.